What you have to do is subtract lambda from the diagonal, and you get this right here. And then you ask yourself the question, under what circumstances is an upper triangular matrix singular? Notice that if an upper triangular matrix has a 0 on the diagonal, then it's singular. From that you conclude that all of the diagonal elements are eigenvalues. How do you then find the corresponding eigenvectors? Well, go and read the solution to this particular homework. So now we arrive at a general 2x2 matrix, and we're going to answer the question, what are the eigenvalues and corresponding eigenvectors of a 2x2 matrix? And this time we're going to do an example first, and then you get to do some homeworks. So let's do this together. The first thing you do is you subtract off lambda times the identity, which is just the same as subtracting lambda from the diagonal elements. Now, the question is, under what circumstances is this 2x2 matrix singular? Well, for that you need to remember that the inverse of a 2x2 matrix was given by this formula on the right here. And hopefully I got that right. Let's see, what did we do? We exchanged these two elements and we negated these elements. But the important part is this right here. And we even gave this here a special name, and that was known as the determinant. If we plug in the matrix where we have subtracted lambda from the diagonal, we end up with this formula right here. We're only interested in this determinant right there, because if that's 0, then it's singular, and if it's not 0, then it's not singular. So we notice that this matrix right here has an inverse if and only if this right here is equal to 0. That is called the determinant of that matrix. So anytime you see the determinant of a 2x2 matrix, it is given by this expression right here, which comes from that times that minus this times that. Okay, now this right here, you can simplify to this quadratic polynomial right here, which you can then factor by examination. That's the kind of thing that you learned in high school. And then what you're interested in is when that is equal to 0. And by examination, you notice that the two roots are lambda equals 2 and lambda equals 3. Once you then pick one of these roots as the eigenvalue, then you plug that into the formula for the matrix. And what you're interested in are vectors that map to 0, vectors in the null space. If you do the arithmetic, you end up with this right here. And just by examination, what you notice is that this column is simply the same as that column right there. And therefore, if you take -1 times that column and you add it to that column, you get the 0 vector. And therefore, one eigenvector associated with this eigenvalue is given by the vector -1, 1. So we get the eigenpair 2, -1, 1. And then the other eigenpair comes from picking your lambda to be the other root, 3. You plug that in. You end up with this right here. You notice that this column is simply 2 times that column. And therefore, if you take the negative of the first column and you add 2 times the second column to it, you get the 0 vector. And therefore, we conclude that the other eigenpair is the pair 3, -1, 2. So let's visualize the eigenvectors and eigenvalues of a non-symmetric matrix. Okay, here we are. Vector x starts pointed in the direction of the first unit basis vector. We've computed 2 eigenvectors, which we have made of length 1. And notice that they point pretty closely in the same direction. We probably should have picked a matrix that had better separated eigenvectors, but we're going to have to live with what we have. If we let this run for just a little bit, then we notice that again x sweeps around the unit circle, and as it does, a times x makes this nice oval. Let's go back to the start and let's step through this. X marches around and eventually points in the direction of actually the second eigenvector, which my guess is corresponds to the larger of the two eigenvalues. And now it gets a little tricky to see what's going on. Let's try to step through this slowly. What you may notice is that the red vector gets slightly ahead of the blue vector, but then slows down and the blue vector catches up again right when they both point in the direction of x0, the other eigenvector. At that point, we're dealing with the eigenvector associated with the smaller of the two eigenvalues. And then we continue. And eventually we point in the opposite direction. Now let's step through that kind of slowly. Here the red arrow roughly points in the opposite direction of x1. And again in the same direction as ax. And then if you look very carefully, you see the red arrow getting ahead of the blue one and then the blue one catching up again, right when it points in the direction of x0, of course in the opposite direction, but that's still in the same direction, just with a negative scaling. And then it continues. So this is an example of where the non-symmetric matrix has two eigenvalues corresponding to two eigenvectors, and the eigenvalues are both real valued. And that's an important thing to keep in mind.